Hello and welcome to lecture 50 of the course Computational Complexity. It's also the beginning of week 10. In the preceding lectures, we saw the complexity class Sharpie, which corresponds to the class of functions that correspond to the number of accepting computations of a non-deterministic polynomial time Turing machine. So some of the examples that we saw was counting the number of satisfying assignments, counting the number of perfect matchings, counting the number of spanning trees, right? Counting the number of cliques of a certain size, and so on. These are all functions that are in Sharpie. We also saw Sharpie completeness, which was defined to be the functions that are in Sharpie and such that all the functions in Sharpie can reduce to this function. So if f is Sharpie complete, if f is in Sharpie, and all the g in Sharpie reduces to f in the sense of an oracle reduction or a Turing reduction, right? So we also so now in this lecture we want to see an example of a Sharpie complete language. So we already saw some examples. We saw that SharpSat, the counting the number of satisfying assignments, is Sharpie complete. We also mentioned that many other reductions such as counting the number of cliques, counting the number of independent set, and so on are Sharpie complete without proofs. I just mentioned that the proofs that show NP completeness, if you look at it closely, you will realize that they also preserve the number of each satisfying assignment corresponds to a certain clique and so on, right? So preserving the number was said to be called was defined as being parsimonious, right? In today's lecture, we will see a language called permanent, right? Which rather a function called permanent, which is a function on a matrix, something like a determinant but slightly different. And you'll see it's even though it's in some ways it's only a small difference, but in some ways it's a big difference, right? We'll see the definition, and then we will see that permanent is in Sharpie and is also Sharpie complete, right? And this was Valiant's theorem from 1979, and that computing the permanent is Sharpie complete even on 0-1 matrices. So even restricted to the 0-1 matrices, computing the permanent is Sharpie complete. So we'll see the proof of that today, right? Maybe some of it may spill over to the next lecture, but we'll see the proof today. And let's see what permanent is. So we briefly had seen the permanent in the lecture 44, where we were trying to check whether a given bipartite graph had a perfect matching. We even so what is permanent? So permanent, it's a summation over all the, so permanent is defined on an n by n matrix, okay? It has to be defined on a square matrix. So it is defined as the summation over all permutations, right? And the product of the ai sigma I. So all the permutations sigma, the product of ai sigma I. So this may seem a bit abstract, so let me explain with an example. So consider this this matrix here, 3 by 3 matrix. So how many so by a permutation I mean, so how many different ways can we permute the rows and columns? So there are 6 ways. So first is the identity permutation, this permutation where each row 1 is mapped to column 1, row 2 is mapped to column 2, and row 3 is mapped to column 3. So 1 time, and then take the product of this 1 times 1 times 0. So that is the first term, right? That is the first term over here, right? Okay. And the second is first row maps to second column, second row maps to third column, third row maps to second column. So that gives you the second term 2 2 2. Okay. Then the third permutation is first row maps to third column, second row maps to first column, and third row maps to second column. So that gives you this 101, right? Okay. And then we have first row maps to first column, second row maps to third column, third row maps to second column, gives you this 1 to 1, right? Then second row maps to sorry, first row maps to second column, second row maps to first column, third row maps to third column. That gives you this 2 times 0 times 0. And finally, we have this first row maps to third column, third row maps to second column, and second row maps to second column, third row maps to first column, which is the last term here, 1 1 2. Okay, so there are 6 terms, one corresponding each of the 6 permutations, right? So, and you just add them up. So for each permutation you compute the product of ai sigma I, right? So the I comma sigma ith entry, so 1 1 2 2 3 3 in the first entry, and so on. So you get the sum. So if you do the summation, you just get 0 plus 6, sorry, not 6, 2 times 2 times 2 is 8, plus 0 times 2 plus 0 times plus 0 plus 2. Okay, so 0 plus 8 plus 0 plus 2 plus 0 plus 2, which is nothing but 12. Okay, so this permanent of A is nothing but 12. Okay, so this is the permanent. It's a rather simple thing once you see how to compute this. Now, how do you compute the determinant? So just to see what is the determinant. So maybe I'll just use another color. So determinant of A is the same thing, but with is the same definition, summation over all the permutations, but then there is a sign component, minus 1 whole power sine of sigma. Okay, then I equal to 1 to n ai sigma I. So the only thing that we do differently is introduce a sign. So if you include the sign here in the above summation, it will be, so you can check this. So there is something called odd permutations and even permutations. So odd permutations will get a negative symbol, and even permutations the sign will be even, so it will be a plus 1. So it will be just 1 times 1 times 0 plus 2 times 2 times 2. So in fact, whatever I have written in the first row are the even permutations, so they are the same. The second row are the odd permutations, so they will get a negative sign. So I am just writing the negative sign outside. So this you can see that is nothing but 8 minus 4 is equal to 4. Right? So this is the determinant computation. So permanent of this matrix is 12 while determinant is 4. Right? Okay. So this, hopefully this is the definition of permanent is clear. And as I said already today, we will see the result that computing a permanent of a matrix is a Sharpe complete problem, even when the matrix is a 0-1 matrix. Okay. So there are a couple of interpretations that will help us. So one is, again, this interpretation we had already used in the lecture 44-45, where we saw that bipartite perfect matching is in RNC. Okay, so one is that we could view this matrix of a 0-1 matrix as a adjacency matrix of a bipartite graph. Okay, so let's say A, B, C be the 3 vertices that correspond to the rows. Right, we are viewing it as a bipartite adjacency matrix of a bipartite graph. So A, B, C are, let's say, are these vertices, and 1, 2, 3 be the vertices corresponding to the columns. Right, so A has an edge. A does not have an edge to 1, A has an edge to 2 and 3, B has an edge to 1 and 3, C has edge to all of 1, 2 and 3, which gives us this graph that is on the right hand side. Now what are the terms here? So you see many terms are 0, but what are the terms that remain? The terms that remain are, maybe I'll just write this down. The terms that remain are, so I'll just write the terms that contribute to the permanent rather are, so I'll just write the 1 1 1, right, plus 1 1 1. So I'm just writing the terms that contribute. Okay, and so So all the non-star entries are the ones that contribute. Okay. So strictly speaking, this is not the sum of the matrices. So maybe I'll just erase this. So permanent is equal to, we'll just 1, 1, 1. So I hope it is clear by when I write it like this. Write the term corresponding to this. Then there is another term 1, 1, 1, right? And finally one more term, it will be I think 1, 1, 1, 1, 1, 1, and this one, yeah. And you can check that these are indeed the only 3 non-zero terms, right? And what happens is that if you look at it, these are the 3 non-zero terms, and these 3 correspond to, maybe I'll just make a bit more space, these 3 correspond to perfect matchings of the above graph. So the first one corresponds to A matches to 2, B matches to 3, C matches to 1. The second one corresponds to A matches to C, B matches to A matches to 3, B matches to 1, C matches to 2. And the third one corresponds to this. A matches to 2, B matches to 1, and C matches to 3. Right? So these are the 3 perfect matchings that these correspond to. And you can see that these are the only 3 perfect matchings of this graph. Right? So the permanent of the 0, 1 of a 0, 1 matrix corresponds to the number of perfect matchings in a bipartite graph. Okay, so if you view the bipartite the 0, 1 matrix as an bipartite as an adjacency matrix of the bipartite graph. So this is one way to view that the permanent of a 0, 1 matrix is actually in Sharpie, because in fact I think I had already mentioned this as an example in the previous lecture. So permanent is in Sharpie. And as with NP-completeness proofs, to show that it is in Sharpie in this case is not that difficult. The main part is to show that any language or any function in Sharpie reduces to permanent, reduces to the computation of a permanent, and that too even for a 0, 1 matrix, right? And instead of since we have already established that sharp sat is a Sharpie complete function, we will show that sharp sat reduces to permanent. And in fact, what we will actually be showing is sharp 3 sat reduces to permanent. Right? In fact, you can check that even sharp 3 sat is so maybe I'll just write this here. Sharp 3 sat is also in Sharpie complete. So I already mentioned that sharp sat is NP complete, Sharpie complete. The same proof applies for sharp 3 sat. Basically, it's about any Boolean formula you can reduce it to, or the Boolean formula that you get as a result of Cook-Levin theorem. You can convert it into a CNF formula and then a 3CNF formula, right? So that's about this. It's not really. So we had done this at the end of the proof of Cook-Levin theorem to show that 3 sat is also NP complete. Same proof works here as well. And what we will do today is to show that sharp 3 sat reduces to the permanent. Okay, so meaning if you can compute the permanent of a 0, 1 matrix, you can also compute the number of satisfying assignments of a 3 sat instance, 3CNF formula. Okay. And for this, another interpretation of the permanent will be useful, right? What is that interpretation? The interpretation is that we can view this graph, this matrix as an adjacency matrix of a graph of a general graph, not necessarily bipartite, but a directed graph. So if you view this as a adjacency matrix of a directed graph, let's see what we get. So the rows are labeled A, B, C, and so are the columns, because it's a 3 vertex graph, right? So A has an edge, outgoing edge to B and C, which I have drawn here, right below. B has an outgoing edge to A and C, right? C has an outgoing edge to A, B, and C. So one of them, so all A, B, C have edges going to each other, and then in addition C has a self loop, which is what I have drawn, here. You can see that. So this is the graph that corresponds to the this adjacency matrix. And in this case, in the case of a general directed graph, you can see that each term of the permanent, each non-zero term of the permanent corresponds to a cycle cover. Okay, so for instance, this corresponds to a non-zero term, and actually this is a cycle cover. So A going to B, right? So maybe I'll just draw it slightly here. A going to B, B going to C, and C going to A, right? So this corresponds to one cycle cover. Just another cycle cover is there's another term that corresponds to the permanent, and this corresponds to the cycle cover A going to B, B going to A back. So it's a cycle of length 2, and then C part of a self loop, right? So this corresponds to another cycle cover. Okay, so each non-zero term of the permanent here corresponds to a cycle cover. So what is a cycle cover? Cycle cover is the covering of each vertex exactly once. It's a covering of the entire graph with cycles, where each vertex is covered exactly once. So you saw that in this case it was like sorry, maybe I'll just erase this. In this case it was like A going to B, B, this is one cycle cover, right? C self loop. So C gets covered by the self loop, and A and B as a two vertex cycle. Or we also saw another cycle where A, B, C are covered by a single cycle, right? The key thing to note is that each vertex is covered exactly once, right? Every vertex should be covered, and every vertex should be covered once and once only, not more, right? And the entire cover should be using cycles. You cannot have a path or standalone edge or anything like that, right? Okay, and in fact this is 0 1 this interpretation is going to be key to our proof that we are going to see. In fact, so this was for a 0 1 matrix. It is just the number of cycle covers of this graph. If G has weighted edges, let's say the CB edge, or let's say the self loop had weight 2, that would have corresponded to the entry here being replaced by 2 if the self loop had weight 2. Okay, the C self loop. So basically the weight will be the corresponding entry in the adjacency matrix, and in that case the permanent will be the sum of the weighted cycle covers. So meaning, so weight of a cycle cover is nothing but product. So maybe I should say product of E in cycle cover weight of E, right? In fact, this is not, number of weighted cycle cover does not make sense, so I will just say sum of weighted cycle covers, right? So permanent is just the sum of these weight of a cycle cover over all the cycle covers, right? So here this is a weight 4 cycle that I have written over here. This is because it's 2 times 2 times 1. Right? So if the graph has weighted edges, it will not be a 0 1 matrix, and the permanent will correspond to the sum of the weighted cycle covers, right? This interpretation is also, this extension is also going to be useful in the proof. So what we are going to show is that sharp sat, in fact I am making this correction, sharp 3 sat reduces to the permanent. And this is so this is not the exact same thing as variance proof, even though in spirit it is the same. There are some small changes in the gadgets. So this is based on two papers. So one by Dell, Husfeld, Marx, Tasleman and Wallen, and one by Blazer, I think 2013 and 14. Both the papers came roughly at the same time. Perhaps they may even have consulted each other while arriving at these gadgets. So in fact those papers do much more, but in fact these gadgets will I feel helps to simplify the presentation, right? But it's essentially the same idea. It's just some minor tweaks in the construction. So the proof will be using gadgets like we saw in the case of Hamiltonian cycle. For instance, we had some reasonably complex graphs which had some things correspond to clauses, something correspond to variables, and we drew a correspondence between the formula being satisfiable and there exists a satisfying assignment. In fact, you may even, if you recall the proof of the Hamiltonian cycle, you may even recall that the number of Hamiltonian cycles of that particular graph that we constructed actually corresponds to the number of satisfying assignments. So it was not just a proof that formula is satisfiable if and only if there is this Hamiltonian cycle. In fact, the number of satisfying assignments would actually, each satisfying assignment corresponded to a Hamiltonian cycle. So it was a parsimonious reduction. In any case, we will use a similar gadgets in a similar spirit. So we will draw a graph which has these these gadgets, and we will show that the permanent of this graph corresponds to some number from which we can get the number of satisfying assignments. Right? So we can roughly divide the proof into 4 parts. One is that we reduce 3-sat, sharp 3-sat into sharp 3-sat balanced. Right? Sharp 3-sat balanced means it's not just a 3-sat instance, it satisfies some other additional constraint. Then this is going to be the main part. The reduction from sharp 3-sat balanced into -1, 0, 1 permanent, meaning it will be we are reducing the computation of the number of satisfying assignments of a sharp 3-sat balanced instance into the computation of a permanent of a matrix with 0, -1 and +1 entries. Right? Remember, we promised that we will reduce it to 0, 1 permanent, but we first go to -1, 0, 1. This is going to be the main part of the proof. Once we have reduced it to -1, 0, 1 permanent, then we show how to move to 0, 1 permanent by also going through an intermediate step, which is 0, 1, 2 up to m permanent, where m is some kind of some positive number. Okay, so we move to a positive range. The weights are from a positive range, and then we move to 0, 1. So the first, third, and fourth steps are rather easy and straightforward. The main part of the proof will be the second step. Right? So let us do it in the order. Okay. So in sharp 3-sat, phi is a 3CNF formula. What is sharp 3-sat balanced? Sharp 3-sat balanced is a 3CNF formula where every variable appears the same number of times positive as negative. Right? So this is easy. The reduction is rather easy because if you look at the clauses, these two clauses, xi or xi negation, if you add it to a formula, the formula's truth value does not change. If the formula was satisfiable, let's say it was satisfiable by setting xi to false, you can add it, it still continues to satisfy. You can add this as a clause. Right? Another clause is xi or xi complement or xi complement. You can add this clause as well. It's still, the truth value does not change. But what happens is the number of times xi appears is now and the number of times xi complement appears changes when you add these clauses. So if it is not balanced, you can add the appropriate number of times to make it balanced. So for instance, if you have a let's say phi that has, let's say, 10x1 and let's say 12x1 complement, right? So it's x2, x3, etc. are there, but let's, so then what you do, you can add. So then you add x1 or x1 or x1 complement and x1 or x1 or x1 complement and phi. So consider, so let phi 1 equal to this. Okay, so phi 1 is equal to this. So now in phi 1, the number of times x1 appears is 14, because phi has 10x1 and phi 1 has 14x1, and number of times x1 bar appears is 14, because phi has 12 and we added 2. So this is it. So as far as x1 is concerned, this is balanced, and like that we can balance out each variable, right? Notice that we don't need to make everything 14. Right? So x1 may be, the balancing value may be 14, for x2 it may be 5, for x3 it may be 2, for x4 it may be 25, whatever, right? So what I'm saying is that for each xi, the number of positive xi appearing and xi complement appearing should be equal. This is important for, this is what I mean by 3-sat balanced. And the reduction, this is just the reduction. So now you have seen how to reduce sharp 3-sat to sharp 3-sat balanced, and you can also see that any satisfying assignment remains a satisfying assignment. Any falsifying or unsatisfying assignment remains an unsatisfying assignment. So as far as the number of satisfying assignments is concerned, there is absolutely no change. So we have, from phi we have gone to a balanced formula without changing the number of satisfying assignments. So that is the first part. Now let us come to the main part. How do we reduce the computation of sharp 3-sat balance to a permanent of -1, 0 and 1 values? Okay, so let's say phi has m clauses, right? Then there are a total of 3m literals, right? Because each clause contains exactly 3 literals, right? And now we know that if you take any variable, the number of positive times that it appears positive as well as negative is the same, right? Right. So you take any satisfying assignment, what will be the number of literals that get, or you take any assignment, forget satisfying, what will be the number of literals that this assignment sets to true? So x5 is if xy is a literal, x5 is a literal, x5, if x5 is set to true, then x5 is a positive, is a true literal. If x5 is set to false, then x5 is a false literal. Suppose the literal is x5 complement, then setting x5 to false makes it a true literal, right? And x5 to false, true makes it a x5 complement a false literal. So whatever it is, the point is that the number of true literals and the number of false literals is equal for each variable, and hence it's also equal across all the variables and across the entire formula. So since there are 3m literals for any assignment, exactly 3m literals will be true and 3m literals will be false. So if you change the assignment, some true literals will become false, some false literals will become true, but still the number of true literals and number of false literals will be exactly equal to 3m by 2 and 3m by 2. The assignments may be satisfying or non-satisfying, but this will always be the case. So exactly 3m by 2 literals are true and 3m by 2 literals are false. Okay. So now what we will do is, we've given the 3-sat balanced instance phi, 3-sat balanced instance phi, we will construct a weighted directed graph G phi, okay, and the weights will be 0, +1 and -1. In fact, it will be mostly zeros and ones, and there will be some -1 for the gadget. such that if phi has k's number of satisfying assignments, okay, phi has k satisfying assignments, then the sum of the weighted cycle covers will be equal to minus 2 whole power 3m by 2 multiplied by k. Okay, this will be the number of sum of weighted cycle covers. So, and which is actually equal to the permanent also, right? This is equal to permanent. Okay, in fact, I have written that below, which is equal to permanent of the adjacency matrix of G5. Right. So, if you compute the permanent, all you have, and you know that based on the number of clauses you can count, you can easily compute minus 2 power 3m divided by 2, and you can divide by that to compute the value k, and you can compute the number of satisfying assignments. So, you just compute, if you can compute the permanent, you just divide it by this minus 2 power this quantity and get k, which is the number of satisfying assignments. So, that completes it, that is the reduction. So, now the main part is going to be how do we construct this graph, right? And the adjacency matrix of G5 will be a 0, minus 1 and plus 1 matrix, a matrix containing exactly these things as entries. Okay. So, what we will show is this: every satisfying assignment, right, that makes P literals true and Q literals false, it will yield a cycle cover of weight minus 1 whole power q multiplied by 2 whole power q, p. So, where p is the number of true literals and q is the number of false literals. Okay. And we have already said that any assignment, in any assignment, the number of true literals and number of false literals are actually 3m by 2. So, this will just boil down to, so in fact, we have seen that in any assignment, not just satisfying assignment, in any assignment, P equal to Q equal to 3m by 2. So, you can see that this is just minus 2 whole power 3m by 2. And there will be non-satisfying assignments, and the cycle covers from that correspond to non-satisfying assignments actually give a total of 0. And there will also be other cycle covers that do not correspond to any assignments, but even they will give a total of 0. So, they will not have individually, they may not be of weight 0, but the construction will be such that they will cancel out and the total will be 0. Okay. So far so good. The goal is to, let me explain again. The goal is to, given a balanced 3-set instance phi, right, where each variable appears in the positive and negative form the equal number of times, to construct a directed graph with weights plus 1, minus 1 and 0, such that the sum of the weighted cycle covers of this graph will be directly related to the number of satisfying assignments of the Boolean formula. Right. So, let us see the gadgets. So, one point I want to mention here, the weight 0, the edges with weight 0, we'll just consider them as edges that are not there. Okay. So, edges that are not there are all edges of weight 0. Okay. So, the edges that are there will be edges of weight 1 and of weight minus 1. In fact, most of the edges, if I don't write the weight, by default it is 1. Okay. So, if it is minus 1, I will explicitly write minus 1. So, there will be a variable gadget, clause gadget and a consistency gadget. So, we will first explain what the variable and clause gadgets are and then go to the consistency gadget. So, the variable gadget is very simple. It contains only 2 vertices, right? There are 3 edges. One corresponds. So, let us say this is for the variable xi. So, there are 2 edges, one going on the top and one going on the bottom. Okay, and all the edges have weight 1. Okay. So, what are the cycle covers of this variable? This gadget, this particular gadget alone. One is So there are two cycle covers. One is this, right? So this goes through the edge marked xi equal to 0. The another cycle cover. So basically there are only two vertices, there are only two cycles, or one cycle is enough, right? So both vertices are covered in both these cycle covers. So one that includes the bottom edge, one that includes the top edge. So the way to understand this or interpret this is that when xi is set to 0 or false, we will consider the top cycle cover, and when xi is equal to true or 1, we will consider the bottom cycle cover. So, and 2 is the clause gadget. Clause gadget is a bit more involved. Okay, so let the clause be li or lj or lk. Okay, this is the clause. So where li, lj, lk are all literals. So each of li, lj, lk could be some variable, let's say x1 or x2 or something, or their negations. So li could be x1, it could be x1 complement, right? So on for lj also. Okay, and this graph that I have drawn here is the gadget. So there are three black edges, like as the outside. They correspond to li being false, lj being false, and lk being false. So if, maybe I'll just write here, if, let's say if li equal to x1, then li equal to false corresponds to x1 equal to false, that is 0. If li is x1 complement, then li is false corresponds to x1 to be 1, right? So I just write one of them so that it's yeah, because then if x1 equal to 1, then li false means x1 complement is false, so x1 is true. Okay. So notice that in this particular gadget, so why does this correspond to, let's try to see why this corresponds to, why this gadget makes sense. So the variable gadgets make sense because there are two settings for each variable, the true and false, and we had two cycle covers corresponding to that. The clause gadgets make sense because of the following reasons. There are three literals. So if you consider li, lj, lk, there are a total of, assuming they can be controlled independently, there are a total of there is only one way in which you can falsify this clause. You must set li to be false, lj to be false, and lk to be false, right? And all the remaining, so there are total 8 ways to assign li, lj, lk, out of which the remaining 7 ways the clause will be true. The one way where all 3 of them are false, the clause will be false, right? So this will have whatever, so corresponding to that, whichever way you set li, lj, lk, as long as they are not all false, you will get a cycle cover. Okay, and all the edges in this graph are of weight 1, so the cycle covers will all be of weight 1. But when li, lj, lk are all false, there will not be any cycle cover. So let us see this. So here, let's say in this particular figure, the one on the left side, li, lj, lk are all false. So which means I consider these 3 black edges, right? So I consider these 3 black edges, and now you can see that there is no way for the cycle cover to include the center vertex, right? Sorry, this changed the vertex color. So there is no way to include the central vertex, right? No way to include central vertex. So there is no cycle cover for this gadget if all the 3 outer edges are considered. Suppose not all the 3 outer edges are considered, right? So which corresponds to not li, lj, lk are not all of them are false. So let us say only one of them is false. Let's say lj, let's say the bottom one is included. So now let us see the cycle cover. If the bottom one is included and these red, so now look at the figure over here, this one, okay. So now the bottom one is included but not the other two. So now let us see what are the cycle covers. So you can include this, but you cannot include the other vertices, right? So what can you do? Other red edges cannot be included. So one way is to use this edge, and then these two can go like a cycle. There are two cycles of length 2, one for one including the bottom two vertices and one include the top and the central vertex. Now look at this one, the second figure. Now I have to include this edge, and we can do this. And then we can do this, right, without including the red edges. Now something similar can be done here. So there is a cycle cover, exactly one cycle cover in each of these cases. Now consider where two of the Li, Lj, Lk are chosen. Again there are cycle covers, right, this one, and I think something like this, right. So there are cycle covers that include all the 4 vertices of this gadget. And let's say if none of the outside vertices are chosen, right, what you can do is you can do this. So you can again do this. So these two, there is a cycle of length 2 between the bottom 2 vertices and cycle of length 2 with the top and central vertex. So just that here in this case, we just use this bidirectional edge to complete the cycle without using the bottom red edge. So whichever way you pick, right, as long as you don't pick all the 3 black edges, there is exactly one cycle cover, right, for the graph, for this gadget. And if you pick all the 3 outside edges, there is no way to make a cycle cover. So now you can see the correspondence. So if you had picked Li, Lj, Lk, all of them, or all of them were false, there is no cycle cover. But in any other case, there is exactly one cycle cover, right? So now the main idea is you will have a variable gadget and you have these clause gadgets, and suppose there was some way to connect these, meaning if you pick a certain cycle cover from the variable gadget, then suppose the same, we have to consistently pick the edges from the clause gadgets. When I say edges, I mean the outside edges, the ones that correspond to variables being false or true. Now suppose there is such a requirement, then you will get cycle covers only when at least one of the outside edges are not picked, right? Because if all 3 outside edges are picked, there is no cycle cover. So you will get a cycle cover only when one of the outside edges are not picked. So only the satisfying assignments will correspond to cycle covers, right? So till now we have not even talked about, all of this are 0, 1 edges. We have not talked about -1, so there is no need to talk about weights as of now. But the main requirement is to somehow connect these, right? To make sure that if you pick x1 to be true in the variable gadget, then correspondingly we should also pick x1 to be true in the clause gadget or clause gadgets. There could be multiple clauses where x1 appears, either in the positive or in the negated form, right? So there should be there is a way to maintain the consistency, right? So we need to have consistent cycle covers, right? So we will ensure consistency using a consistency gadget, and we will have to allow for other cycle covers, but what we will do is to make sure that the other cycle covers, they contribute to weight 0, okay? So the totals add up to weight 0. And one question that you may ask is, one variable may appear in multiple clauses. So x1 may appear in xi may appear in multiple clauses, but then there is only one variable gadget. So we cannot enforce multiple clause gadgets cannot enforce consistency with single variable gadget. So we need multiple copies of this. So what we do is we will have a different clause gadgets, right? So we have something like this. So we replace it with this kind of a the picture in the right side. So the point here is that if xi was chosen to be, let's say we want to pick the bottom part. Let's say we want to pick the top part for this, and then the bottom part for, let's say we pick the bottom part, xi equal to 1 part, and now there are two additional vertices, but then they can be covered by the self loops. Similarly for let's say if xi equal to 0, like I'm talking about, so this is the correspondence. Similarly, if xi equal to 0 edge was chosen, then you will choose the opposite of this, and there are self loops in the bottom. And this particular gadget, the one I have drawn, supports xi as long as xi appears at most 3 times. If xi appears 4 times, you can have one more of these self loops, right, and one more edge like this, one more vertex like this, right, and likewise we can do for each of the variables. Okay, so now let us move on to the consistency gadget. So the consistency gadget will connect the relevant part of this, the relevant part of the variable gadget. So let's say this is corresponding to clause 1. It will connect this part. This one says xi equal to 1 with the relevant part of the clause gadget. So the clause gadget will say somewhere xi equal to 1, because maybe there is some literal that where xi was appearing as xi negative or xi complement. So when that xi complement has to be made false, xi has to be 1, and we need to ensure consistency. Okay, so basically it boils down to, if xi equal to 1 was chosen here, right, we should also choose, let's say this edge was corresponding to xi equal to 1, right. We should also choose this edge from this gadget. So how do we do that, right? So it boils down to, if this edge is chosen, the other edge also should be chosen. If this edge is not chosen, the other edge also should not be chosen, right? This is what we want. So now let us forget the gadgets that we have seen so far, at least temporarily. We have two edges, uv and u prime v prime. The requirement is that if uv is picked, u prime v prime should be picked, and if uv is not picked, u prime v prime should not be picked. And this are kind of independent things. It's not immediately possible to connect them. So what we'll do is we'll add an intermediate vertex or 3 intermediate vertices and add some connections between them, and this will help us connect them. So there are multiple cases, and we will see that all of them turn out to be the right way. Okay. So what we will show is that, let's say uv corresponds to, let's say, some xi equal to, or let's say, let me just say uv corresponds to x2 being 0, and this one was some u prime v prime was, let's say, some li is false. So this means that li was just x2. So x2 equal to 0 has to be same as li is false, right? Okay. So when uv and u prime v prime are both selected, so this is what we want, this is what this gadget will accomplish. Again, the sum of this is a recap, but there's a bit more details. When uv and u prime v prime are both selected, this means there is a variable that is set in a certain way that causes a literal to be false, right? There is some false literal, right? Let's say there is a false literal, and this results in a cycle cover of weight -1. Okay, so we'll see how this happens. Weight -1 when neither uv nor u prime v prime are selected. So which means x2 was not 0, and this li prime, or sorry, li complement was not selected, which means the literal li was set correctly, right, satisfying that clause, right. In that case, there will be 6 cycle covers, right, and some of them will have weight 2. The total weight will be 2, and there will be other cycle covers also, and all of them will add up to weight 0, right? They will cancel out. Okay, so this now hopefully tells you why we get this quantity, right? Earlier I said this: if there are p true literals and q false literals, the cycle cover should have weight -1 power q to 2 power p. So each true literal gives 2 and each false literal gives -1. So the total cycle cover weight is the product of all of this. So -1 power q times 2 power p. Okay. Okay. So this establishes this for each satisfying assignment. And we have already seen that when the assignment is not satisfying, there is no way to cover the central vertex of the clause gadget. So that will not even contribute anything, because there will be no cycle cover corresponding to that. So the cycle cover is only contributes for the only satisfying assignments contribute to cycle cover. The weight will be -1 power q times 2 power p, where p is the number of true literals and q is the number of false literals. Okay. When I say true literals, it's the literal that is set in the correct way. So if the literal is x1, then x1 setting to true is a true literal. If the literal is x1 complement, x1 setting to false is a true literal. Okay. And we have already seen, since phi is balanced, the number of whichever assignment you do, the number of true and false literals will be same, which will be 3m by 2. So the total, each satisfying assignment contributes to a weight of, since p equal to q is equal to 3m by 2, it will be 2 minus 2 whole power 3m by 2. This is the contribution of one satisfying assignment. If there are m satisfying k satisfying assignments, the total contribution is this: minus 2 whole power 3m by 2 multiplied by k, right. So now for the second part of the proof, what we need to establish are these three properties. When uv and u prime v prime are both selected, the cycle cover will be of weight -1, and neither of them are selected, there will be 6 cycle covers that give a total weight 2. Other cycle covers somehow cancel out, right. So this is the gadget. So notice there is only one vertex here with weight -1, all the one edge with weight -1, the self loop at the blue vertex. All the other edges have weight 1. And when I am drawing this two-headed edges, right, so these are actually between this green and blue, green and blue here as well. So there are two-headed edges, so which means there are two edges, one going up to down, down to up, right. So let us see the cases. Consider the case when both uv and u prime v prime are selected. So which means in the original graph, so the original graph is in the left hand side, you come to u somehow like this, then you use this edge and then you go out of v. Similarly, you come to u prime like this, then you go to v prime and then you exit like this. Now right, so now let us see the total weight here. This corresponds to using this, right, using this. So now all the edges in the gadget are already covered except for the blue vertex. All the vertices in the gadget are already covered except for the blue vertex which we introduced, right, and we need to cover that. So what is the way to cover that? There is only one way. We just include this self loop. So the total weight of the cycle cover is whatever was the total weight multiplied by a -1. So this corresponds to -1. and there is no other way to include anything else, right? So this tells us how this claim was true. Now let us see this. Let us see neither uv nor u prime v prime are selected. So which means in the original graph, you come to u and you go out somehow, you come to v, you go out somehow. We don't use these edges. Come to u prime, come to v prime, right? Something like this. Same thing over here. So now these three edges, vertices that we introduced, the green and blue vertices, somehow they need to be covered. What are the ways in which we can cover this, right? So if you look at it closely, there are multiple ways, right? One way is simply to use self loops at each of the three vertices, right? So that will correspond to a weight of -1. That will correspond to a weight of -1. Or you could use, so I'm not going to do all the examples. You could do these two edges, and then you could use a self loop here that will again give a weight of -1, right? Or you could use a self loop here and then these two edges like this, so that will give +1. And if you look at it closely, there will be another cycle cover where there is a self loop here and these two are picked, and there will be two more cycle covers, one where you do something like this and one where you do something like this. So a total of 6 cycle covers, the first 2 being negative and the last 4 being positive. So you can verify this. So I'm not explaining the details that slowly, but I hope it is very clear. So the total weight of all this is +2. So now this part is also clear. Then neither uv nor u prime v prime are selected. There are 6 cycle covers of total weight 2. Now what about other cycle covers? Let's say uv is selected but u prime v prime is not. Something like this, which means in the gadget this happens. So now the top green vertex is already covered, but the bottom green vertex and the central blue vertex are not covered. So there are 2 ways to cover it, right? One is you could use the 2 self loops at the green and blue vertices, which will give a total weight of -1 because it's -1 multiplied by +1. Or you could use the edges across. You could have a cycle of length 2 which will give +1. So the total weight is 0. The +1 and -1 cycle covers cancel out. And the same thing happens when u prime v prime is selected but uv is not. And then there are some other weird cycle covers, something like this, right, where you come to u and then you do this and then you somehow exit from v prime. So and then something, so these do not have any corresponding things to the original graph because the original graph does not have an intermediate vertex between u and v, right? If there is a cycle cover like this in the new graph, this fortunately does not really cause any problem, because how can you connect the top path to the bottom path, right? So the one way to connect is through, you can do this kind of thing, and where the blue vertex has a self loop, and that corresponds to a cycle cover of weight -1 because of the self loop. Or you could do something like this, right, where the blue vertex is included, which and without, so self loop does not come into play here. So this corresponds to a cycle cover of weight +1, right. So this, so total weight is -1, where the green to green you draw an edge and the blue one is covered with a self loop, so -1, and 2 is +1, where you go from the green to the blue and then to the next green and then follow this. So the self loop does not come into play, so the weight is +1, so total weight is 0. So these, and you, similarly you can think of other cycle cover, that's where you go into U prime, then V, then you go climb up top and then exit through V. But none of this does not really impact the total of cycle covers, because the total weight is 0, right. So what is happening here is that only the consistent cases where both UV and U prime V prime are picked, or neither UV nor U prime V prime are picked, they give the positive total weight. And whenever one of them is picked and the other one is not, and other nonsense cases such as this, there is no right. So there is no all the cycle covers cancel out, so leading to the total weight 0, right. So which is what we said over here, right. So all that remains is to note that all the positives, all the true literals, right, which have correspond to cycle covers of weight 2, all the false literals correspond to cycle covers of weight -1, and the rest of the cycle covers don't really, the nonsense cycle covers, and only the consistent satisfying assignments contribute to the cycle cover, right. So the total weight is -1 whole power q times 2 whole power p, where p is the number of true and q is the number of false literals. But then we know that the number of true and false literals are always 3m/2, regardless of whether the assignment is satisfying. So the total is -2 whole power 3m/2, and we get different cycle covers for each of the satisfying assignments. So this completes the reduction from sharp 3-sat balanced to -1, 0, 1 permanent. Okay. So just to summarize, we reduced, we said what is sharply complete, we explained what is permanent, right. We saw the correspondence between permanent and the bipartite graph perfect matching of a 0, 1 permanent. Then we saw the correspondence between permanent and the sum of the total cycle covers, sum of the weights of the total cycle covers. And then we saw the first two parts of the reduction, where we reduced sharp 3-sat to sharp 3-sat balanced, where each variable appears in the positive and negative form equal number of times. And second, we saw that when such an instance, such a formula is given, where each 3-sat instance, where each variable appears equal number of times in positive as well as negative, positive and the negative form, right. You can reduce it to a permanent, is -1, 0, 1 permanent. This was done by constructing a graph with weights 0, -1 and +1. So as I said, 0 corresponds to all the edges that were not there, +1 and -1 we saw, right. So such that if you compute the permanent, you can count the number of satisfying assignments of the 3-sat formula. And we explained the gadgets of this reduction: variable gadget, clause gadget, and the consistency gadget. And what remains is to show that you can reduce the -1, 0, 1 permanent to a 0, 1 permanent, and that, I said, follows two fairly straightforward steps. But since this video has probably gotten fairly long, I will show that in the next part. Since this reduction is kind of a bit long, I didn't want to split it into 2 parts, but the remaining parts I will show in a separate video. Thank you.